tire under your car right now is holding up over 1,000 pounds. Using a contact patch with the road roughly the size of your hand, it looks like a single solid ring of rubber, but inside it's actually built from more than 20 different layers, stacked one on top of another like a hidden sandwich of steel, fabric, and rubber. It has to grip ice, survive scorching asphalt, and flex millions of times without failing. Yet it starts its life as a soft, sticky slab that couldn't hold its own shape if you set it on a table. And somehow the difference between a tire that lasts 80,000 miles and one that fails in a blowout comes down to something almost nobody thinks about: the precise chemical bond formed during 8 minutes of intense heat and pressure, in a step most drivers have never even heard of. That shouldn't be this complicated for something that's just supposed to be round and black. So how do factories turn raw rubber, a handful of chemical powders, and coils of steel wire into the one part of your car that's actually touching the ground at a scale of over 2 billion tires every single year? Let's step inside and find out. Almost nobody has seen a tire before it's a tire. It doesn't start as a black rubber ring at all. It starts as dozens of separate raw ingredients, most of which look nothing like the finished product. Pale slabs of natural rubber, barrels of oily synthetic polymer, sacks of jet black soot-like powder, spools of brass-coated steel wire, and rolls of fabric cord that look more like something from a sewing shop than an auto parts store. By the time it leaves the factory, every one of those ingredients will have been blended, shaped, wrapped, and literally baked together under enough pressure to crush a car, fusing into a single object that has to survive years of abuse without ever being inspected from the inside. What's stranger still is that a modern tire isn't really one material at all. It's closer to 25 different components engineered to work as one, each with its own precise recipe, hidden inside a shape so familiar, most people never stop to wonder what's actually in it. A tire begins with rubber, but not just one kind. Natural rubber is harvested from rubber trees, mostly grown on plantations across Southeast Asia, where workers make thin diagonal cuts into the bark and collect the milky sap, called latex, as it slowly drips out overnight. That raw latex is then treated with acid to make it coagulate into soft sheets, which are washed, rolled, and dried before being shipped to tire factories around the world. Alongside natural rubber, tire makers also rely heavily on synthetic rubber, a man-made polymer created from petroleum byproducts through a chemical process that lets engineers fine-tune properties natural rubber can't offer on its own, like resistance to heat or better grip in wet conditions. Most modern tires actually contain more synthetic rubber than natural rubber, blended together in different ratios depending on which part of the tire is being built. Beyond rubber, a handful of other ingredients transform the final product entirely. Carbon black, an extremely fine soot-like powder made by burning oil or gas in a low-oxygen environment, is mixed in to reinforce the rubber and give tires their familiar black color. Without it, tires would actually be a dull, off-white shade, closer to the color of an eraser, and would wear out far faster. Silica, a sand-derived compound, is often blended in as well, especially in tires designed for better wet weather grip and lower rolling resistance. Sulfur plays a smaller but critical role, since it's the ingredient that later allows the rubber to be chemically locked into its final shape. Various oils, resins, antioxidants, and accelerator chemicals round out the recipe, controlling everything from flexibility in cold weather to resistance against sunlight and ozone cracking over years of outdoor exposure. Then come the structural materials that give a tire its actual shape and strength. Steel wire, coated in brass to help it bond with rubber, is used to form the bead, the tough inner ring that grips the wheel rim, and steel belts are woven to reinforce the tread underneath the surface. Layers of fabric cord, made from materials like polyester, rayon, or nylon, are embedded inside the sidewalls and body of the tire to hold its shape under pressure, acting almost like the skeleton hidden beneath the rubber skin. In total, a single modern tire can be built from more than 200 individual raw materials, all of which have to arrive at the factory in exact, tightly controlled quantities before a single tire can be built. Mixing the rubber compound. Everything begins in a massive machine called a Banbury mixer, essentially an industrial-sized dough mixer, strong enough to knead raw rubber, carbon black, silica, oils, and chemical additives together under intense pressure and friction. As the ingredients churn, the friction alone generates enough heat to soften the rubber into a thick, dark, taffy-like mass. Because different parts of a tire need different properties, the tread needs grip and wear resistance, while the sidewall needs flexibility. Factories don't make just one rubber compound. A single tire design might require 10 or more distinct rubber recipes, each mixed separately, cooled, and set aside for its own specific part of the tire. Extruding and calendaring. Once mixed, the rubber compound destined for the tread and sidewalls is forced through a machine called an extruder, which squeezes it through a shaped opening the way a pasta press forces dough into a specific noodle shape, producing a long, continuous strip of rubber with the exact tread profile already built into it. Meanwhile, the fabric cord and steel belt material go through a separate process called calendaring, where thin sheets of rubber are pressed onto both sides of the cord under heavy rollers, essentially laminating the rubber directly onto the fabric or steel, so the two materials become one combined sheet, ready to be cut into precise strips. Building the bead. Long strands of brass-coated steel wire are wound together into tight, round bundles called bead cores, essentially small steel hoops, one for each side of the tire. These bead cores are then wrapped in rubber and reinforced with additional fabric, forming a tough, rigid ring that will later grip the wheel rim tightly enough to create an airtight seal, strong enough to withstand the tire being mounted, inflated, and driven on for years without ever slipping loose. Cutting and assembling the components. All the different rubberized layers, the body plies of fabric cord, the steel belts, the tread strip, and the sidewall rubber, are cut into precise strips at specific angles, since the angle of the cord layers directly affects how the tire will handle and flex once it's on the road. These components are staged and delivered, often on overhead conveyor systems, to the next stage of the process, where they'll all come together for the first time as an actual tire shape. Building the green tire. This is where the tire finally starts to look like, well, a tire, though at this stage it's referred to as a green tire, meaning uncured and unfinished. A tire building machine, essentially a rotating drum, allows a technician or automated system to layer the components in the correct order. First, the inner liner, an airtight rubber layer that replaces the need for a separate inner tube. Then the body plies, followed by the two steel bead rings, and then the steel belts and tread strip on top. As each layer is added and the drum expands, the flat layered assembly gradually takes on the toroidal, donut-like shape of a real tire. At this point, the green tire is soft, slightly tacky to the touch, and noticeably lighter and less rigid than the finished product. It could be reshaped by hand, which is exactly why it isn't a tire yet. Curing and vulcanization. The green tire is placed into a curing press, a heavy steel mold shaped like the inverse of the final tire, complete with a tread pattern carved into its interior surface. Inside the press, a rubber bladder inflates from within the tire, pressing the soft rubber outward against the mold with tremendous force, while the entire assembly is heated to roughly 150 to 180 degrees Celsius for somewhere between 8 and 15 minutes, depending on the tire's size and design. This heat and pressure trigger a chemical reaction called vulcanization, in which the sulfur added earlier forms cross links between the rubber's polymer chains, transforming the soft, moldable green tire into a rigid, durable, weatherproof final product. Before vulcanization, the rubber molecules exist as loose, tangled strands that can slide past each other, which is why raw rubber is soft and stretchy, but doesn't spring back reliably. After vulcanization, those strands are chemically locked together into a connected network, which is the entire reason a finished tire holds its shape and bounces back after being compressed, instead of staying permanently dented. Removing flash and initial inspection. As the tire comes out of the mold, It often has thin, hair-like traces of excess rubber called flash or spew left over from tiny vents in the mold that allow trapped air to escape during curing. Automated trimming stations and sometimes hand tools remove this excess rubber, leaving behind the clean, finished tread pattern and sidewall markings, including the brand name, size, and load rating, all of which were actually molded directly into the rubber during the curing step itself, rather than printed on afterward. Uniformity and balance testing. Every finished tire is mounted onto a testing machine that spins it at high speed, while sensors measure for any variation in stiffness, roundness, or weight distribution around the tire's circumference. Even a few grams of imbalance can cause a noticeable vibration at highway speeds. Tires that fall outside acceptable tolerances are flagged and pulled from the line, while tires within spec often receive a small paint dot marking their high point, a reference mark that tire shops later use to balance the tire correctly against the wheel. X-ray and visual inspection. Because so much of a tire's structure is hidden beneath the rubber surface, factories routinely use X-ray imaging, similar in concept to a medical X-ray, to look inside a sample of finished tires and check that the steel belts, bead wires, and fabric plies are all positioned exactly where they're supposed to be, with no trapped air pockets or misaligned layers that could cause a failure down the road. Alongside X-ray checks, tires undergo visual inspection for surface defects, and select samples from each production batch are physically cut apart and examined cross-section by cross-section, sacrificing a handful of tires so that the rest of the batch can be trusted. Final quality and durability testing. Beyond the factory floor, sample tires are subjected to extended real-world simulation testing, including high-speed endurance runs on massive indoor drums that spin the tire continuously for hours or even days at highway speeds and above, as well as controlled tests that measure how the tire performs under heavy load, in wet conditions, and at temperature extremes. Only after a design passes this battery of tests does it move into full, ongoing mass production, and even then, random samples continue to be pulled and tested throughout the tire's production life to make sure nothing has drifted out of specification. By the time a single tire has gone from raw latex and chemical powder to a finished, tested product ready to ship, it has been mixed, extruded, layered by hand or machine into more than 20 separate components built into a soft green shape, chemically transformed under intense heat and pressure, trimmed, balanced, X-rayed, and stress tested. And the entire process, from raw material to a finished tire rolling off the line, typically takes less than a day from start to finish. Here's the detail that surprises almost everyone. A single passenger car tire can be built from more than 200 distinct raw materials and around 30 separate rubber compounds, each formulated slightly differently depending on exactly where in the tire it ends up. The compound used in the tread, which needs to grip the road and resist wear, is completely different from the compound used in the sidewall, which instead needs to flex constantly without cracking. It's essentially like building one object out of 30 different purpose-built materials, all fused seamlessly enough that the finished tire looks and functions as if it were a single solid piece. And the vulcanization step is even stranger than it first appears. Before curing, that green tire is soft enough to reshape with your hands, and the sulfur added to the rubber compound is what makes the transformation possible. During those few minutes of intense heat, sulfur atoms form new chemical bridges directly between neighboring rubber polymer chains, and once those bridges form, they can't be undone by heat or pressure again. This is why a used tire can't simply be melted back down and reformed into a brand new tire the way steel or aluminum can be melted and recast. The chemical structure has permanently changed. Instead, old tires are typically shredded and repurposed into things like playground surfaces, rubberized asphalt for roads, or industrial fuel. Or in some cases, ground down into crumb rubber and blended in smaller quantities into new rubber products. Even the tread pattern itself hides more engineering than most drivers realize. Those grooves aren't just decoration. They're precisely designed channels meant to funnel water out from under the tire in wet conditions, since a tire traveling at highway speed in the rain can encounter more than a gallon of water per second beneath its contact patch. And without those channels, the tire would simply ride up on top of the water layer, and lose contact with the road entirely, a phenomenon known as hydroplaning. Once a tire passes final inspection, it's coated with a light dusting or spray, often a talc-like powder or a specialized mold-release compound, both to prevent tires from sticking together in storage and to give the surface a clean, uniform finish. Size, load rating, speed rating, manufacturing date, and a Department of Transportation identification code are all molded directly into the sidewall, allowing anyone to trace exactly which factory and even which week a specific tire was produced in, which becomes critical information in the rare event of a safety recall. From there, finished tires are stacked, banded, and loaded onto trucks and shipping containers bound for auto manufacturers, who mount them on brand new vehicles rolling off assembly lines, as well as tire retailers and warehouses that supply replacement tires to drivers everywhere. A single large tire factory, running continuously, can produce tens of thousands of tires in a single day, turning raw latex, black powder, and coils of steel wire into millions of finished tires a year. Each one built to carry a vehicle's full weight, absorb the shock of every pothole and highway seam, and grip the road in rain, snow, or scorching heat for tens of thousands of miles before the entire process begins again with the next batch of raw material. That's how a soft slab of tree sap, a handful of black powder, and coils of steel wire become the only part of your car actually touching the road, built from over 200 raw materials, layered by hand and machine into more than 20 hidden components, and permanently transformed by 8 minutes of heat and pressure into something that can't be undone. Strength at this scale isn't an accident. It's the result of getting dozens of separate recipes exactly right, fusing them into one object, and trusting that bond to hold at 70 miles an hour in the rain for years at a time until now.